Today we're going to continue talking about the buffer overflow attack. We talked about the very simple example. In that example, I didn't even show the input, right? We just have a fixed string longer than 12. Okay, and this is the example that you're going to see in the lab. Okay, so the code here is we have a function here. Okay, we have a function foo here. Okay, which does string copy. Okay, and the size of the buffer is 100. In this example, okay, in the lab it's different. Okay, in the lab the size is different. Okay, so I don't want you to use what I teach in a class and just blindly use in the lab. I'm changing those parameters, so you still have to know. You need to know how I do that, not just copy my data. Okay, so that was the intention. And then in the main function, okay, and it actually opened a file we call the bed file. Okay, so and the content of the file is going to be actually 200 bytes of that file is going to be read into this string, and then this string is going to be passed down to the foo function and copied to the buffer, which is only 100. Okay, so you have 200 of data here and 100 of data, the memory storage there, and so that's actually a buffer overflow. Okay, so the buffer, if you look at this, the foo, okay, this is the foo, the stack frame. Okay, the buffer is here. Okay, but buffer only have 100 bytes. Okay, but when we do the copy, the string has 200. Okay, as long as I don't have a 0 inside. Okay, and you know if I have a 0 inside, and that will terminate the string. Okay, it doesn't matter how many I copy. Okay, so and this will copy all the way from here and eventually override the return address. Okay, and we talked about that. And also, I'm also going to put my code. I'm going to put my code in this bed file. Okay, so when that is copied, everything is going to be copied to the stack, including my own code, and that's how my code get into the memory. Okay, so this is the buffer that I actually. This is the buffer. This 200 bytes long. Okay, this will come from the bed file. Okay, whatever you put in the bed file, okay, the first 200 character will be read by the program, and eventually through the string copy and copy to this buffer starting from this place. Okay, so and that's how if you can put your code at the higher end, and this code will be actually be put in here. Okay, and you don't need to write the code. In the lab, we have already written the code for you. Today I will explain how that code works. Okay, so and then once you actually override this, if you did everything correctly, okay, and then when this function returns, it will take this return address and jump to whatever this return address points to. Okay, so therefore, in order to make this work, you need to override this field and with a particular value. Okay, all the other fields it doesn't matter. Okay, the value it really doesn't matter. Okay, but this. Of course, this code that does matter, okay? But this is the most critical part, okay? And you need to be able to use an address here, okay? You need to make this return address point to somewhere here, okay? We put another no-op in here. So from the last class, we pre-fill this entire buffer with 0x90. That's no-op. So if you can jump to any of these places, eventually no-op basically does nothing. We just go to the next instruction. Okay. So if you go to here, eventually it's going to go to the entry point of that code, and your code get executed. Okay. So that's what we covered in the last class. Okay. Conceptually, it's very simple, but in order to do this, you need to solve these two challenges. Okay. One is where is this? So whatever I put in here will be copied into the return address field, okay? And I need to figure out where should I put in here, right? I know my file, this bed file starts from here, okay? And when you read from the beginning of the bed file. So I need to accurately, this one needs to be very accurate. If you actually made 1 byte and a mistake, and you won't be able to copy the right thing. So you need to find out this address, the distance is not, and then this is location. There should be 4 bytes. We are using a 32-bit machine. So 4 bytes, and now you also need to decide what to put inside these 4 bytes, what to put in here. Okay, so as I said, the content here should be the address of something here. But you need to find the address. That's what we want to do. Okay, in your lab, actually the majority of your task is to do this. First, calculate the distance. Second, find out what put in here. Okay, and then the rest of them we already place for you. The field this with 0x90 is already in the code. We did that for you. So we wrote a program called exploit.c. Okay, that program's goal is to generate this file, the bed file. Okay, there are actually not non-typable character in the bed file. So we don't want you to just type the bed file. Okay, some of them they are binary number and they are not typable. Okay, so that's why we write a code to generate the content. The majority of the code is already written, including this code. It's in this code. You need to add a few lines of code to basically solve these 2 problems, 1 and 2. So here, this is the buffer we're creating in the exploit.c file. And this one will be actually saved to the bed file. Okay, this one will go to the bed file. Okay, so that array initially we just fill this with all 0, and then we copy this malicious code, okay, into this region. This is the beginning of the buffer. Okay, and now your job is to find out where should I put that return address, okay, and also what the content of return address. So this is, as I said, 1 and 2. So how do you calculate this one? How do you figure out this? Any idea? From here to here. So if I go back to the program, okay, so this will be from the buffer. So the distance is actually from the buffer to here, to the return address here. This is the distance. We need to know this number. So how do you figure that out? How would you propose to figure it out? The code is here. We assume you have a source code. We assume you have a copy of source code. You can play with that, whatever you want. Okay?
You have know the buffer length, so you can calculate these buffers have how much
okay.
size in the.
Very good. That's a good approach. So we know the size is 100, right? So we will say that's just this way will be just 100, right? That's a good try. Okay. So what did I say in the last class? The actual distance here. What did I say? 100 plus 1. Yes, compiler may add some additional thing in there. Okay, this 100 is a good guess, but it's not an exact number. Okay, and you're going to find out in your lab it's not going to be 100. It's always going to be 100 plus something. Okay, in your case we didn't put 100 there. We didn't put we put 24 in there. That's in the lab, and it's going to be 24 plus something. But you need to be very, very accurate. As I said, if you miss by 1 byte, and this won't work. Okay, so a rough, it's not going to. Yeah, you can try. You can try, right? If it doesn't work, you can try. You can do that. Okay, you can always try. But in this lab, I want, if you have the source code, I would like you to be able to accurately and find that number. Okay, what would you try? So we need to do an investigation to find out what this number is. We know it's about 100 plus something. Okay, so you have a source code. You have a code. You can GDB that, right? So you can actually run this code in the debugger. And inside the debugger, you just need to print out this address. Okay, print out this buffer address, and also print out something here. What do we print out from here? So this is the buffer address. You can in the GDB you can just p and this address of buffer, and that gives you the address of the buffer. Here you want to p something. What is the most important thing here? EBP, okay? EBP point to the 4 bytes below the address, right? So there's a previous frame pointer. EBP point to that. So we just need to print out EBP. So you will get these two numbers when you do the debugging, and you minus that, you get a distance. Okay? That's how you calculate distance, and this distance is fixed. Okay, so this distance, and when you run your code, your copy of the code, okay, and as long as you use the same compiler, okay. If you don't use the same compiler, it's going to be different. Okay, but if you use same compiler with same option turned on, and then the distance will be the same. Okay, so in our lab, and we are using the same compiler. Okay, so we allow you to compile this into a debug the program, and then figure that out. Okay, so that we solve that problem. Now, how do we find this address for here? It's also in the debugger, right? We have already seen something here, right? What is EBP? EBP point to here, right? So now if you already know EBP value, so what value should I use for here? Should it be okay, that's good. So EBP points to here, the frame pointer. 4 bytes above is return address. Okay, and then 4 bytes above this, right now is no op. After overflow, everything above is actually becomes no op. And this is actually the first place, the first address you can use, but anything above and should work. Okay, so EBP plus 8, that's your actually the first address you can use. Okay, so that's all the second problem. Okay, but the assumption is when you run your code, the memory is the same as this setuid program. Okay, so that assumption. Okay, and that assumption is true after we turn off the countermeasure. Okay, you always have to remember turn off the countermeasure. The countermeasure I will talk about is called address randomization. Okay, and the first thing you need to do is turn that off. Always remember, anytime you reboot the machine, you have to turn it off. Okay, if you just save the state, that's okay. Okay, if you reboot the machine and shut it down, and you need to set that again. Okay, that's not permanent. Okay, so otherwise, and this address will not be the same. Okay, EBP won't be the same. Okay, so that's one countermeasure. Okay. So any question about this? So here basically you have this and you have this, okay, and you construct, you get the value and put in there, okay, and this is the distance, okay, everything is constructed, and then the exploit.c will save that into the bat file. Okay, so you need to run the exploit.c, and then you run that vulnerable program. Okay, the vulnerable program is going to be the setuid program. Okay, and then if everything works, you're going to see the pound sign. Okay, if you still don't believe it, type ID inside that, and you're going to see the RUID still the seed, but EUID becomes 0. Okay, so that means you already get the root. Okay, so that's what you will do in the lab. Okay, now the next thing is how do we write the shellcode? Although in this class, I don't require you to write the shellcode, but writing the shellcode is actually a very fun part. Okay, so as I said, there's a competition in the past, and to compete for the shortest shellcode you can write. Okay, so So let's look at the code that we're going to write is to get us to run a shell command, right? That's what we want. And we want to have a run command. Shell command is what we want. Now let's see, why can't we just write a C code? I can write a C code to use exec-v to run /bin shell, right? I can do that. Why can't I just compile this into C code? I get a program called a.out. Why can't I just copy this entire a.out into my buffer? Assuming my buffer has enough space. Why can't I do that? Okay, and then I'm going to find this engine point, the main function somewhere. Okay, I don't know. I just random pick a place. Okay, and then I'm just going to jump to that. That's my main function. Right? Main function doesn't always start from beginning. Okay, so this is binary. Okay, this is binary. I'll just show you. Okay, a main function somewhere. So I just need to copy this entire thing into that buffer a.out. Okay. And then I'm just going to find this, where's my main function? And then I'm just going to RT, override RT to jump that main function. Okay. Can I do that? Can I? This looks like a very obvious approach, right? I just write this and.
One problem is that when you fit into the buffer.
It doesn't fit in the buffer?
Right.
Assuming we have enough space. Assuming I have enough space. Okay. So although this file is quite large, you can see this such a simple code is 7,000 bytes. Okay, more than that. Okay. So assume I have enough space for that. Okay. So can I do that? Okay. So when you type a.out in the command line, okay, so the OS is going to load the program. OS that's loader. The loader does not just put this binary in the memory. Okay, this is what we are doing. We just copy this in the buffer. But loader doesn't just only do that. Okay, that's actually the easiest part. Loader does a lot of things. Okay, loader is going to set up your memory. Okay, for the process. Okay, and loader is going to actually do the linker, right? Remember, if you ever need to use actually a link library, if that's dynamic link library, the loader is going to trigger the linker. The linker will do the link. So before you actually main function get triggered, there's a lot of things going on here. Okay, those are not data. A lot of them are code. Okay, so before the code even hit the main function, many other things has been executed. Okay, so by the time it get here, all the initialization things are done by the OS. Okay, so now if you don't do that, your code won't run. Okay, you need to set up everything, and then you can say I'm going to jump to the main function. So, but in our case, we just directly load into the memory. We skip all the initialization. Okay, so your code is not going to run. Okay, so that's the first thing. The second thing is, did you see 0 in this code? You see a lot of 0, right? Okay, now string copy is going to stop at here. Only the first 6 bytes get copied. The rest of them is not. Because string copy sees 0 and it thinks this is stop. So your entire code is here, but you have a first 0 in this I think the 8 bytes. So basically the rest of them will not be able to copy into the buffer. Okay, it is in your bed file, but it will not be copied because string copies stop in here. So that's another thing we need to deal with. We cannot have 0. So how many 0 do we have if we don't look at this code? If we just look at this code, how many 0 can you identify in this code? How many? Where? Show me where the 0 is. If we turn this into a binary, okay? Right now it's a C code. C code has some binary in the code. If I turn that compiled into binary, some 0 will be also in the binary, right? So tell me where this 0 might be. Okay? Any?
A string?
right? As I said, at the end of string, that's 0. Okay, it doesn't show here, but that's 0, and you cannot skip that 0. Okay, that 0 will be in your binary. Okay, so that first 0. What else? Anytime you say none, that's 0, right? None is 0. Okay, that's a 0 here, and that's a 0 here. Okay, and also in order to do this, you may not have 0. Okay, because if you have a 0 here, and in a compiled binary, they will not add 0, because add 0 is redundant, right? So they will just directly use the edges of that. So you may not have that 0. Okay, but even if you have a 1, you think there's no 0, right? If you see 1, right, where's 0? How can this 1 contain 0?
Address.
No, this 1. So if I need to add these edges of this plus 1. I need to plus 1. In that plus 1 instruction, 1 is going to be represented as 0, 0, 0, 0, 0, 0, 0, 1. That's the integer 1. This is integer, so, sorry, yeah, so 4 bytes, yeah. Actually 4 bytes. So even though you don't see 1, you don't see 0, but in the binary, they have to actually spell out the entire 4 bytes. And that's the way you got to see 0 in there. Okay? So there's a lot of opportunity for 0 to be in your code. So even if you can compile this, even if you get this load of things to work, you still have to resolve those 0. Okay? So a requirement for the shellcode is you should not have single 0 in there. Okay? Whether this will be copied to string copy or not. Okay? Because if the memory copy is not string copy, the 0 doesn't matter. Okay? If it's a memory copy, then the 0 is not going to be the end. But in order to call the shellcode, and you should not allow the 0. Okay? So because now your shellcode can be used in all the scenarios. Okay? Any questions? So this is actually a shellcode example, okay? So let me just make it large. And this is the one that we're going to use, okay? And in the lab, and you don't need to write. So I will just explain what this does, okay? This shellcode and all the shellcode, what they do is they will just call the exec v. That's what they do, okay? Exec v is a system call, okay? The goal is to call the exec v system call. The way to call a system call, okay, is different from call function call. Okay, call system call. What you do is we'll go from the back, from the end. Okay, int. Okay, different color. So int 80. So interruption 80, and that is the system call. Okay, so when you call the say interrupt 0x80, that means you interrupt the CPU. And you tell the CPU, and I'm going to interrupt you, and this 80 means I want you to look at the system call table. That's a table, okay? Every system call have an engine, okay? Each engine points to their code, okay? So basically I said, why don't you look into your table, system call table? I'm going to tell you the number 11, 0B, okay? 0B, that's 11 here. That's where the exact V is. Okay? If you want to call an open system call, and it's going to be some other number, I don't know what the number is, but you just provide a different number, and you say, I want to call open. Okay? So this 2 line, so it basically triggers the CPU to go to this engine, and then invoke whatever this points to. Okay? That's a system call table inside the kernel. Int 80 triggers that. Okay? That's the system call part. You need to set this the AL register and to be 11. And so that's how you pass this number, 11. Okay? So, and you want this system call to invoke the shell, right? So exec v has a 3 parameter. Okay, remember we talked about the exec v, the function. That function actually eventually mapped to the system call. Okay, whatever the parameter you use, eventually is going to pass to the system call. So remember, what are the three parameters here? The first one is a command. Okay, the first one is /bin shell. The second one is basically the argument, right? We're going to actually contain the argument. The argument v0 should be basically the name of the program. Okay, and the third one, environment variable. Okay, so in this case, we don't care about the environment variable. We don't want to pass environment variable. We just put a 0 in there. Okay, so now when you invoke a function, we push these things into the stack, right? That's how we pass this to a function. When you call system call, you cannot push this into a stack. The way to call system call is different from call function call. You have to pass the data and using a different mechanism. In this case, we pass that through the register. Okay? So exec v is going to look at those register, get the information from the register. So this 3 register will be used. Okay. So this will be EBX, ECX, EDX. And EAX is used for and this AL is a part of EAX. Okay. So EAX is used to save that number. Okay. And so these 3 registers need to be set correctly. Okay. Once you set them correctly, now you can run this, and now the system call is going to execute that program for you. So everything here really is to set these 3 registers. That's what they do. Okay. So now let's look at how they set this register. Okay. Let's look at the easiest one. Okay. This one, the CDQ is actually they can. Okay, let's forget about CDQ. How do you turn the EDX into 0? How do you put a 0 in the EDX? EDX and 0. Okay, would that work? Did you see 0? Did you hear 0? Right? Anytime you hear 0, that's no, okay? Cannot have 0 in my code. So and 0, that should be one of number will be 0. Cannot be there. How can I? I can move 0 to the register because that's a 0. Okay? So that's what? Minus? So you put say 1 to EAX, you minus 1. Right? Okay, so remember 1 is going to be 0, 0, 0, 0, 0, 1. So still you have 1. You have 0 inside. Okay? Okay, say again. Then you decrease. That's going to take a long time. Yeah, if that works, he's saying just put maybe 1, 1, 1, 1, 1 inside of this, and then just decrease it for many, many times, right? Until it reaches 0. But that's an easy way to do that. Yeah, so he's on that, okay, but it's much simpler with the XOR, right? If you XOR one thing with itself, what do you get? You get 0, right? Any number XOR with itself is 0, okay? So that's what you do. You can XOR, and actually that's the first statement, XOR EAX with EAX. That's basically turn this EAX into 0. And you can do the same thing, XOR EDX with EDX. You turn that into 0, okay? So basically, if you're not familiar, 1 XOR with 1, you got 0. 0 XOR with 0, you get 0. Okay. So anything XOR with itself becomes 0. Okay. So that's how you generate a 0 in this register. Okay. But this code, I didn't write this code. Okay. I use example. Okay. And the author of this trying to reduce the size of this by 1 byte. XOR is 2 bytes instruction. So this also tried to turn that into 1 byte. So he or she, I don't know who the author is, found this instruction will achieve the same goal, but using 1 instruction. That's why I said there was competition for that. People fight for that 1 byte. Okay, but I don't want you to actually spend too much time on that. So I'm just using that to show you there are many ways to do that. Okay, and this is, I don't even know what CDQ does. Okay, CDQ eventually a side effect actually. It's the main purpose of CDQ is not to set the EDX. The side effect actually set the EDX to 0. Okay, so this one set. Okay, so now let's look at the other part. Okay, so now this two part is more complicated. So now we need to provide the address to this field. The EBX has to contain an address. Remember the trouble that we went through just to find out address, right? Remember the trouble? Right now everything is on stack. Now to find that address, we went through a lot of trouble, right? We put a no op, right? We do the GDB, we try to do a lot of things like that. Now you put some string on the stack, and you said I also need to get its address. And that's going to be complicated. Okay, so getting this address into here is going to be complicated. When you put this code onto the stack, it's going to be very difficult to know where this string is. So very difficult to find out where exactly the string is. Okay, so we had trouble even to find the entry point of the function, the code, right? And that's why we put a lot of no op to help us. Now you need to find exactly where that is. Okay, so and this code actually uses very good tricks. So it doesn't actually place this in here and statically. It uses dynamically. So inside of code, it actually put this data in the stack. Okay, so basically push the data into the stack, and then you can read the stack pointer to find where the location is. So that's actually the idea here. So the code is to push the data. Okay, I don't know where the data will be, but when I push the data into the stack, I can read from the stack pointer register, which is available. It's a register. I can read the value, and then I can just assign that value into EBX. That's how I get the address of the string. Okay, so that's what it does. Okay, let's see what it does. Okay, the first few lines, XOR EAX. So EAX now becomes 0. Now push EAX. So let's draw the stack. Okay. So the stack right now is here. That pointer, stack pointer. Stack pointer register is ESP. Okay, that's the ESP register. Okay, so let's start from here. Push EAX. That means 0 is going to push into there, right? So 0 is going to push into here. That's how they put the 0 in the memory. Okay, so you don't see any 0 in your code, right? But now 0 is inside now. Okay, next step. Push this. Okay, this is a number which represents //sh. Okay, so there's a // Let me just use a different color. //sh. Okay, I will explain why double slash. Okay, and the next one is push/bin. Now you know what this code is doing, right? It's actually trying to push this. If you just look at this with /bin /sh, push it and the string into the memory and end with 0, and that's what this code is doing. Okay, the reason why they use a // in the system, the double slash is equivalent to one single slash. Okay, so what they want to do, they need 4 bytes here. Okay, and /bin got 4 bytes, /sh only 3 bytes. They need 1 more byte. Okay, so they can do the push. This got to be 4 bytes. You cannot push 3 bytes. That's why we said if you want to push one into the memory, you have to put 0, 0, 0, 0. You have to be 4 bytes. Okay, so it basically constructs 4 bytes here, and double slash is equivalent to single slash. So that's why, and you see the double slash here. So this whole thing constructs this. Now every time you push, ESP is going to move. ESP now is going to move. Now you know the ESP value, right? Now you know the address of this buffer. Next things, you move ESP into EBX. That's exactly what we want. ESP nonce in EBX. So now EBX point to the string. Okay, we solved the first problem, right? And we don't need to guess. Now, next things, what it does, let's look at the next thing. The push EAX again. So let's see, EAX is going to be pushed. So continue on. 0 is going to be pushed inside. Okay. Now, push EBX. What does it do? Push EBX. When this is here, now ESP is going to be here. Now push the value of EBX. The value of EBX actually point to here. This address. It push this EBX. That means the address is not going to be pushed in here. Okay. Now I'm going to move this on to ESP here. Now this address is going to push in here. That means this is not going to point to here. What this code is trying to do? So you get an array here. The first element point to this address. The second one is 0. What is trying to do? It's trying to construct the argv. That's exactly what argv is. The argv 0 should be / bin sh, right?
Yeah.
That will be the command. argv1, we don't have argument. That should be 0. Should be none. And this is an array, and that's exactly what it's constructing, right inside the stack. So you got this, you got this. Now you just need to know the argv's address, which is ESP. Right? Next things, you move ESP to ECX. That's exactly what happened. Now ESP moved to ECX. So we got everything, right? So it looks like a magic. So it's really taken a lot of this skill to be able to write a code like this. Okay. And then the EDX, and which will recover. Once you did that, now you can code the int 80 and with 11 as the system core number. Okay, and then this will execute. Okay, and you can see this is a machine code here. This side is a machine code, and this side is basically the assembly. And you can see there's no 0 in here. Okay, I think the total is about just 20 bytes also.